Good morning. Just we start with the announcement. Probably you would already seen the email that our TA is going to have a tutorial, and it's he will review the concept, review the quizzes, and also assignment questions for the first half of the semester, right? So he will do the summary statistics, probability, and also random variable. So if you have a question, please feel free to email him in advance so that he can prepare better. But of course, you can bring your question to the venue. You can either attend in person, which is a big lecture theater room, or you can attend in Zoom. Or if you don't have time, you can. He will upload the record anyway. So there would be should not be a conflict of time. So it will be the time will be next Thursday, so next Tuesday, 9:30 to 6:30 to 9:30 at LSB, C2. So that would be the case. So, but any question you can always ask him to see what can be done over there. But that was the first announcement. Second announcement to be made will be our self quiz is already released. So if you have time, you can work on it. As I emphasize, the quiz are by participation. So you do it, you get full credit. So make sure you do it by the end of semester. So there's two announcements. For those who arrive late, I just repeat the announcement we make by our TA about the optional tutorial that you might attend. Okay, on top of the quiz. And so then we are ready to start our class. Which will be the what we're doing is we will finish this sales slide on estimation and start on the some introduction to a long chapter, hypothesis testing. So for estimation, just a very quick review. So the idea is we are trying to guess what the population parameter, such as mean, variance, skewness, kurtosis. Okay. These are numbers that we're trying to guess. And how we guess is through estimator. And estimator are simply statistics. Okay. And remember, what is statistics? Statistics are function of sample. And sample are random variable because they are collecting from the population. That means that our estimator are random variable, and they will have the mean, the variance, they will have the distribution. Example will be sample mean is to estimate population mean. Sample variance is to estimate population variance. Okay. But do note that once we collect the sample, we no longer have probability because once realized, it become a number. And we can't use probability from that on. We have to use the term confidence. So that would be several key things here. And there are two types of estimator. One is point estimator, which you would just make a single guess. An interval estimator, you are not making a single guess, you're making a bunch of guesses. The reason is the single guess is good because it's something simple. You just give me a number. But how precise is this is not entirely clear. The interval estimator tells us how confident or how precise our point estimator is, because this incorporates, as you know, the standard deviation of the point estimator, right? So basically, you would add plus and minus 2 times of the SD, right? So that is the main idea behind. That will include the 95 percentage confidence of what we want. So that is a usual. I just repeat again, right? Usually, if you give the best guess with the point estimate, you give a conservative and aggressive range. That would be our interval estimate. So the point estimator in our class would tell us that two of them, actually three, right? Well, sample mean for population mean, sample proportion for population proportion, sample variance for population variance, right? And there are three important properties for good point estimator: unbiased, efficient, and consistent. But just quickly, unbiased means that if you have a sample, you estimate, and another sample you estimate, okay? And each sample will come out with one estimate. Average of this estimate end up with the parameter you want to guess. Okay, so that would be unbiased. And you know that these are sample mean and sample variance are unbiased. And efficiency, here it means that among all the unbiased estimator, the variance lowest. So it's just like closer to the target. In this case, A is more efficient than B. And last one is consistent. Is eventually when the sample size get very large, it eventually no different from almost there, you get the parameter. Okay. And if under the case is unbiased, it just simply means the variance shrink to 0, right? As we said, the sample mean is very good, so I don't think we have to justify that. And this, as promised, now we explain at topic 5 why topic 1 we have many sample versions. The sample mean, the sample variance is a MS1. This version is good as is a unbiased estimator of population variance. Same for the funny formula for sample skewness and sample excess kurtosis. So those are unbiased estimator, and that's why we have those. Okay. Although we didn't prove those, but they are all unbiased. And later you will see when we do interval estimator or confidence interval, we will keep using this standard error of mean, because this is standard deviation of the sample mean, right? Because we will plus or two plus minus 2 times of this will get us 95%. With binary data, the sample mean becomes sample proportion, so there's nothing new here, okay? Except that because the mean and variance are connected, so once we have unbiased estimate of the proportion, it actually gives us another estimator of the sample variance. Okay, and this is the one we use. Okay, but if you try to think carefully, it is biased, and this one should be used instead. But this doesn't really matter because n is large enough, so it doesn't really a big deal for us. Okay, so we will keep using this as many textbook has been using. Okay, so interval estimator. So we focus on sample mean. Of course, later we talk about sample proportion because it's a special case also. The idea is that we want to include precision measure for the sample mean, right? We want to know if I was given the sample mean, I want to know how good it is. To do so, we need to either invoke central limit theorem or normality assumption to make the sample mean has a normal distribution. Why? Because by doing so, we can quantify what we call the interval estimator idea. What we want is the following. We have a sample mean here, right? We go left and right by M. And we want to go symmetrically, extend a little bit in such a way that this range, okay, this interval with length 2m will have high probability it will include the population parameter mu. Okay, suppose the mean mu. Okay, I don't know where the mu is, but mu may be anywhere, right? Because I just don't know where, right? But mu may be actually something here, right? I don't know where it is. I want this is inside rather than outside. Okay, but you would notice that it is the interval is a random variable, not the mu. Okay, so the idea is like this, right? X bar follow normal with center and mu, variance sigma square over n. Okay. And the sample we got, right, is somewhere here, 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 anything here, right? Anything can happen, right? But if this happen, the procedure asks us to go left by M and right by M. Okay. And in this particular case, if M is this shape, this interval will include the mu. Okay. And because this is normal, so X bar can be anywhere. X bar can be very far away, right? For example, X bar can be like somewhere here. If you draw M left and right, then this will not include mu. Okay. So how can we decide the M, right? If the M is large enough, then that we can always include mu, right? But what we want is we want this to be measurable. So we want very high probability that we would include the mu, right? So we want 1 minus alpha probability. So alpha usually is 0.1 0.05 or 0.01, right? So how do you get M, right? The idea is rather simple. It's because we construct from X bar, go M left and right. C, we include mu, but this equivalent to you just make mu go left by right by M. Okay. And as long as your X bar is realized within this range, right, it would be there, right? So that means that I want this probability to be 1 minus alpha, has high probability there, okay? And we know this is standardized, this is normal. So if this is alpha, okay, and that means that this guy is just Z alpha over 2 sigma over root n. Why? Because this is just you just 1 minus alpha, and this is alpha over 2, right? And because it's converted the distance of this, it just this multiplied by how many SD, right? Because that is the idea of standardized normal, right? It's just how many SD from the mean, right? So that's why M is exactly this number, right? So that's why our interval estimator is X bar plus minus Z alpha over 2 sigma over root n. So that is the main thing we want to say, right? We cover in the last class there, right? So you have to remember this formula, okay? Even though if you don't fully understand, this is something that should be in your cheat sheet, right? Right, so that would be the idea. The proof is already in the slides. If you care to read, the proof is already here. Just line by line is not. There's no high power math here, so just the proof here. Okay. So so this example, let me go over that again because that would be crucial for your understanding. So just remember, this is the formula here. Okay. For this question, X bar is 3. Right here. Sigma is 4. Small here. And 64 is here. Okay. You want 95% confidence, which 1 minus alpha is 95, which imply alpha is 0.05. That imply alpha over 2 is 0.025. And C alpha over 2, simply in Excel, we just norm dot S dot inverse 1 minus 0.025, right? So it's 0.975, right? So that would give you 1.96. Okay? So you just plug in all the number there, right? But roughly speaking, it's just 2, this number, right? 2 times, this is standard deviation of the sample mean, right? Remember this, right? This is standard deviation of the sample mean. So basically, the interval estimator is very simple, right? Just the sample mean, you go left and right by 2 SD, right? That's very simple formula, right? 95%, right? Go left and right by 2SD. If 90%, right, then you go 1.64 left and right, right? So that will be is that okay? Now, the next thing we also talk about in the last class is, suppose we don't know sigma, which often the case, then you have to use S instead, right? And you have to make additional assumption where what we call normality, the underlying is also a bell. Okay? And if you're willing to make the same assumption, the formula will be the same. It will be just the sample mean plus minus some number, of course, more than 2 now, but you can replace it by S. So now, let's see the example again. So just remind you the formula here, plus minus T, n minus 1, alpha over 2, S over root n. So X bar is 3, so it's 3 here. Okay. Just to remind you that your 3 will be your point estimate, your best guess. And your sample size is 20, so it's here. Right? S is 12, it's also here. What remains is this guy. Yeah. But there's nothing deep here. This is just T dot inverse, right? 95%, again, means 1 minus alpha is 5%, right? The alpha is 5%. Alpha of 2 is 2 from 5%. And then that means 1 minus alpha 2 is 97.5. So it's 0.975. And because of T, you have to tell which is n minus 1, which is 19. Once you do it, they will give you 2.09. Okay, so once of that, now you will see your guess will be 3, and the minimum you guess is negative 2.6. The maximum will be 8.6. Okay, so that will be your guess. If you are allowed to, you have to ask what is the best guess you get, what is the most conservative and most aggressive one. Okay, so that would be the idea. Okay, is that a question? Is that okay? And after that, we talk about the binary case. One of the good things about binary case is we don't have to rely on T. It's always normal. Okay, as long as n, you are willing to see the data with NP and n minus P more than 5, then this always apply. And the caveat at the beginning always apply to your case anyway. For business application. So that means that this formula, we always use it directly. Okay. So let's apply again. Okay. To do it, just write down the formula here again. P plus minus C alpha over 2 square root P1 minus P over N. So this is the question, right? You can imagine a lot of application, like you ask how many people would like to buy your product, right? And you ask 64%, and turn out that a quarter of people like your product, right? And a quarter of people like your product is a good estimate, but it is not precise enough, right? And at the end, you end up with 15% to 35%. So it's a 10% range. Okay. Not very precise, but at least this is what you get. Okay. But let's see how we compute this 10% range. Why the ME is like 10%. Okay. So we know that this is a quarter. So this is a quarter only. Okay, this is a quarter. This is quarter, right? This is 3/4, right? And it's 64, right? The only thing is this guy, and you know 95% is already, you know, it's 1.96, right? Say, so that everything is very simple, right? And then up this guy, the margin of error is 10%, right? So your precision is up to adding 10% and minus 10%. Is that okay? So here comes a slightly little bit more interesting problem now is, so far we are given our sample size, right? The sample size is given. Someone decided, okay? But the usual case is you are the one who decide, right? If you collect data, right? Because you want to decide it. But what is your choice? Your choice would be, you want to know at the end how precise your results is. Basically, you have to control your margin of error, right? If you want a smaller margin of error, you need to have more sample, right? So you can see here, when I have 64 sample size, the margin of error is like 10%. Okay. And later you will see this is indeed not a coincidence. And in general, this is what you get when you have around 100 sample size for binary data. Okay. So you will have to choose your precision, and then it will determine your sample size magnitude, whether it's 100 or thousands or 10,000s. That will be the goal of the rest of the 10-page slides, okay? Which we call sample size determination. Okay. To make our life easy, we focus on the case where we know our population variance. Okay. Otherwise, we have this T, then we have to solve some complex calculation. Of course, now you have a computer, you can do it. But we focus on the case where sigma square is known. Okay. If not known, then we have to solve more complicated math, which is beyond the scope of our calculator. Okay. So suppose we know it. This is a margin error, right? So we used to know this phi number, and then we calculate this ME, right? So we know the thing on the right-hand side, we calculate left-hand side. This is what we do, right? And this is, we say this is our interval estimator. This is the interval, right? But now we reverse the process, right? Suppose we want to have our end outcome first. We design our ME, okay? We design our ME. And we give our alpha, right? It's 5%, so it's known as well. And this known by our problem. We know this 3, then we figure out what is n. Okay, just reverse the process. We have our desired margin of error. Okay, we go back to ask ourselves, can we find n to achieve our desired precision, right? Because ME is how precise we are, right? If the smaller the ME, the more precise our interval, right? So now what we need to do is to change the subject, right? How to do this math here? You multiply both sides by root n. So sorry for the high school math. So root n is gone, right? So what we have is root n ME equal to C alpha over 2 sigma, right? So we left this formula. And now we divide both sides by ME, right? So ME is gone. So what is left is this guy. Root n is equal to sigma alpha over 2 sigma over ME, right? And because these are all positive, okay, it's the same, you square both sides, and you end up with this guy. And why I have a ceiling function here? Because n must be integer, right? So I would find the smallest integer to satisfy that, right? So this is what you do in your primary school, right? You get a decimal number, you round up to the nearest integer, right? So that is the math we get here. So that is the goal, okay? So let me illustrate that in an example. Now, assume that the population follow normal with standard deviation 10, okay? Sigma is 10 here. And after this, I will tell you how to come up with a good estimate of sigma. I'll discuss a little bit. But first, our formula said the following. N is Z alpha over 2 square, right? If you still remember, sigma square over ME square, right? So sigma square is 10 square. So that is what you see here. This 1.96 we do many times already, so I'm not going to repeat, right? And ME is you decide to be within 4 of the population mean, right? So you end up is 24.01, so you need 25. So you can see if you want to improve your precision, right? So from plus minus 4, say, to plus minus 2, right? Then you would have quickly make 4 times of the size, become n would become 100, right? So you would do, if you do that, right, your sample size required will be around 100. Right? So that is how you would do the calculation, right? Just plug all the numbers in, right? Because this is, just to remind you, right? This is 1.96 square, and this is 10 square, and this is 4 square. And this 4 square is your decision. Of course, The question is, how do we get the 10, right? When you actual practice, how to get a 10. And remember, we have what we call the 68, 95, 99 rule. What was that? Is 99% of the data will be within 3 SD, right? If it's normal. So that means that if you look at the data, look at the max and the mean, or you have some knowledge about the max and mean data, that should essentially means they will be 6 SD, right? 3 SD for the left, 3 SD for the right. So we took the range and divide by 6 will give you the SD, right? For example, well, I get 10 here because I would think, actually, in my mind, I think of IQ. IQ usually should be within 70 to 130, right? You talk to normal population. Then the SD will be 10 because the range is 60. 60 divided by 6 is 10, right? So if you have a good idea what is the maximum and what's the minimum data, which is easy to guess, I think you guess the max and minimum, right? And divide by 6, and you're done, right? Of course, if you have some previous data, of course you can guess, right? But this is, you can do it without collecting data, right? We don't have the data, right? We don't have correct data, so we don't know the S, right? Because you ask, okay, can't I guess this from my sample standard deviation, right? But the thing is, you haven't collected data. How can you guess, right? But you may have good idea what are the mean, what are the max, right? So that is something that easily accessible. And since you assume normal, so that means that you would already have the 3 SD rule would apply, or 2 SD will apply already. Is that okay? I hope of course, this is beyond the scope of what we're saying, but just to see how you apply in practice. Okay? If there's no further question, we go to the next one. Which is same, but we do proportion, right? The proportion formula is this guy, right? If you know the pi, this is what we get, right? And and the thing is, now the only trouble is we don't know n, right? we decide this guy. We decide this guy. We decide this guy is something from our prior knowledge, okay? Then we can fix our n, right? The math again is not complicated. You again multiply both sides by root n, right? So this is gone. This is gone. And you divide both sides by ME. The M is there, right? This is gone. Okay. So what you left is just square root n on the left hand side. Right hand side will be Z alpha over 2 square root pi 1 minus pi over ME. And then what left is you square both sides, you get this formula, right? Because everything positive. So this formula would imply that, right? You get a ceiling function again. As I said, this is just integer problem because this can be a decimum number. You just run up, right? If 11.1, you become 12. If 11, you just write 11, right? If 11.2, if 11.5, you write 12, right? If 12.1, you write 13, right? Just the smallest number integer that is larger than the number you got. Okay. So let's plug in the equation, and then we'll have a break. Okay. So that is very simple formula, right? Because this formula n is equal to z alpha over 2 square pi 1 minus pi over me square, right? So this is a formula. And we know our old friend here, if you 95%, this is 1.96 square, right? And it has been known that pi is 0.4, right? So I don't know how you get it, but someone tell you this 0.4. Okay, we're here. And after the break, I'll talk about if we don't know this 0.4, how can we proceed? Okay. But I assume we know 0.4. Okay. And sometimes you know it because you have some rough idea what's going on. For example, right, you do an election pool in the US, you pretty much know that around half of people would like Trump, half people hate Trump, right? So that would be already there. Okay, so you don't have to worry too much when you collect the data. And ME is our choice, which is 0.01, right? So just put all the number there. You have 92.1. You run up 93. So you 93 sample to get precisions of 0.1, right? So at the end, if you get, say, number is 0.3, there will be 0.2 to 0.4, right? If you get the sample proportion is 0.45, then at the end, you got range will be 0.35 and 0.55, right? So that would be the idea there. Okay? So if you have no further question, I suggest with a break. Okay? And then after the break, we'll talk about if we don't know pi, how can we proceed? Okay? So with break, let us have a you reply so. We break a 15 minutes. So, um, just a very gentle reminder before we do the real reply again is some admin thing is next Tuesday we have a TA optional tutorial section in LSBC2. Already announced by the TA. I think you get the email. So just if you have a question, please feel free to ask there. I'm pretty sure you have a lot of questions. For your assignment, your quiz, and also any other material you want to ask, he'll be there. And then also he'll be delivering by Zoom, so you can ask question. Okay. Or you can just email him for the further details. Okay. And the quiz 4 has been released, so you remember try to take a look on those questions that you know better about our material. And today we will finish this chapter estimation. That means that the next set assignment will be released on the way. I am asking my TA to check a little bit to finalize the assignment. So we should be releasing on early next week. So should be before our holiday where you go hike on next Wednesday. Probably you know it's a Chongyuan Festival. So you when you hike, you can bring your assignment there and do something when nothing to do at the peak of the hill. Right? So it'll be fun. So let's see the you reply, see if anything to say. Oh, so there's some advertising. Please come to the booth, Chongqi tonight. 有嘢飲, okay? 有好嘢飲, so there's good thing to drink. So if you want, go there. I don't know what they serve. You have to ask. I even don't know what event is. Maybe something Halloween. I don't know. Whatever. Uh, uh, tutorial will cover that. So please ask the TA for this one because he and she will handle the assignment. Okay. You can also ask him in tutorial. I think he'll go over that. If you have any particular question of an assignment, please email the TA because I think he will do it over it. Super tired and want to sleep. Yeah, I think everyone is same, right? Everyone's tired because Friday. Finally, finalize all midterms. Okay. I'm glad for you. Okay. And same for me because I finalized on midterm because I know midterm to begin with. No midterm for. Still have 2 midterm for you? Yeah, sorry. It's already 2/3 of semester already, right? The 8th week. So you still have some midterm. I'm so sorry about that. But I never give a midterm when I teach a class. If I co-teach with others, then other give midterm. But when I ever teach, I never give a midterm. Because I think midterm is not very useful. You are very busy. So I just add quiz, and quiz is optional, right? More or less optional, right? So just do it. So of course, if you want me to give you a real midterm, I can do that. But I can do it next year. Of course, not this year. But you can let me know. Difficult. Is it my class? But if you think difficult, just to know, we are not asking you to derive. So just remember the formula. You know where to apply. That's not different from accounting, right? My class is not different from accounting. just put the number there. You just apply the formula, put it there. It's there, right? So if you are able to pass your accounting exam, you should be able to pass my exam, right? It's even easier than accounting, right? I would say, right? Accounting has more tricks. We only have one trick. You see this problem, this is the only formula. You just plug in the number, you need to calculate, and you're done. So actually, I would say my class is easier than accounting class, I would say, right? But of course, if you understand the details, same for accounting, you want to understand why actually is both of them are not that easy. Understand why, say, depreciation, why you have the strict rule or what we call double, whatever rule, I forgot. But that is a double exponential, I forgot. But there's an exponential thing. I mean, sorry for my very rusty accounting. That's the thing. The only thing I remember is strict depreciation. That's the best I can remember. But of course, the behind is just math, right? So whether it's good. Um, Sample size for mean. Yeah, this is 1.96. Good. Yeah, that's right. The speed is okay, except one person think I'm a little bit too bad. But the score is 4, so I'm very glad. Two people think I'm not lazy. So it will be increasingly harder and harder because we're getting more abstract. Because looking at sample size is hard to think without a proper, some imagination. But I would say when you do the assignment, you know how to work out the assignment, then you should be fine. Okay? Because that's something what I'm asking at the end of semester as well. Oh, luckily, today we have less than half of you feel very tired. And also some of you is good because I think midterm is over. So we have a much more straight line instead of exponential curve. So I'm pretty glad that we're not very tired. I mean, somewhat tired, but of course it's Friday effect. But run out of dumb jokes to share. It's okay. I think last year people just copied jokes from the web and put it there. And also there are some stupid jokes, local jokes from Canton. But I guess this year we are more serious students, so we don't have stupid jokes. High pleasure. Oh, sorry about that. Yeah. Well, when you think your life is difficult, at least you have health. Because now I'm coughing, I'm sick for a week, so I've noticed that being healthy is already very good. If you feel a pressure, already you actually good because you don't feel sick. So I think that is a kind of hopefully consolation to you. Yeah, final Friday. So at least next week you have 2 holiday, right? One is the climbing the hill holiday, right? Second is trick or treat, right? So I don't know whether you still do that. No, no one do that. Trick or treat, Halloween, right? So so I will bring candies, right? So you will see it for the celebration. I mean, of course, you are feel free to dress up, have for fun purpose. Uh, as actually my kid go to primary school, they all have the fun day, right? As well. Um, Now get back to our main business. Where am I? So, as promised, what happened if we don't have historical proportion, right? So I want to ask yes, no question, right? Suppose I want to know how many people still like Anson Lo I don't know whether I know answer no, because I only know it because I read some website. They say, oh, his concert tech cat still a lot. So the question would be, is there many people want to see a Mura concert, right? Yes or no question. Or are you tired, right? So this question, right? Are you tired is a question, yes or no, right? And I don't know now because before the midterm, maybe 90% of you say tired. But after the midterm, if I ask tomorrow, if you have good sleep, is it going to be how many sample I need to get? So the answer would be very simple. If I don't know, I use the worst case scenario. The worst case scenario turned out to be half. Remember, when we talk about the Benoni, the worst case scenario in terms of variance is 1/2, right? So that's why pi times 1 pi max is a quarter. Why? Look at the graph here. I prepared for you. This is high school math. The horizontal is pi. Vertical is pi 1 minus pi. Okay? When pi is 0, 0 times 1 minus 0 is 0, right? When pi is 1, this is 1, right? And you know, pi times 1 minus pi is negative quadratic, so it will be a curve. And the biggest will be 1/2, right? And 1/2 times 1 is 1/4. So we'll use the worst case scenario to maximize this. So that's why if you don't know, we use 1/2. Okay? 1/2 is the worst case scenario. Okay? That means that when we do the calculation, as example here, I have no evidence about population proportion. I want 95% confidence. I want it within 1%. So the formula is this, right? N equal to Z alpha over 2 square pi 1 minus pi divided by me square. Me is 0.1. This is 1.96 square. And what we use, we don't know. We use half and half, right? And at the end, you get 97. So if you want the precision is within 0.1, then you use around 100. Okay. And actually, we can see there's a good approximation there. Look at the numerator. The numerator is actually close to 1. Why? Because this guy is 2, right? 2 squared is 4. 4 times a quarter is 1, right? So that means that N, if you look at 95% confidence, will be similar to 1 over me squared. So if you want the precision to be 0.1, right? That's 1 over 10, right? So that's why you have 10 squared, which is 100. right? So if you want the precision to be 0.01, then you can easily calculate that will be 10,000, right? Because if you want the ME is 0.01, which is 1 over 100, they imply N will be 100 squared. It's 10,000, right? So if you want ME to be 0.03333 is 1 over 30, say 1 over, right? That means that N will be 30 squared, which will be 900. So why I want to pick out this particular 900 case is look at US election poll. You done any election in the US. They always ask for around 1,000. Okay? And end up the margin error is like 1 or 2%, 2 to 3%. That's common here. And that's why in the US, although it's a very big country, they only need 1,000 observation every time. Because when you ask binary data, doesn't really matter. No matter how big the country is, you just ask 1,000, sufficient. Say even in China, billions of people, you just need 1,000 data. You don't need to scale up that much. And in Hong Kong, right, look at recent survey, a lot of them is also about several hundred to 1,000. Why? Following this, right? If you want it to be within 3, it will be like this. Okay? Is that okay? So you can easily, when we look at 95% confidence, you can easily calculate this 1 over ME squared is the answer you need. Okay? Is that okay? So because you would ask, sometimes some of you ask me how much sample I would need for my survey. That is the answer I already give you. Okay? If you just ask yes, no question in your survey, that's very simple. That you come up with this number, right? So you never need more than 1,000, right? Of course, if you want, maybe you want to be very precise, maybe you want to have 10,000, and that 10,000 is almost the best you need. You don't need further. Okay? To end this chapter, I want to tell you 2 functions. I don't find it very useful, but I just put it because you can see it. Okay? And this is trying to give you the margin of error directly. Okay? So remember, margin of error is like this formula or this formula. Okay? And if you write confidence norm and 5%, they will give you 95% confidence margin error with sigma 4 and 64 will give you this number, right? So this is just saying norm S inverse, right? 0.975 times 4 divided by SQ RT 64. Right. Let me show you the Excel. And also give you the same number. So I show you that they are exactly the same. Okay. So that actually prove you this is exactly what the calculator behind. And that's why I don't find it very useful, but except you calculate this a lot, right? And but of course, this is also convenient because you don't want to damage your head by calculate 1 minus alpha over 2 and 1 minus this thing, right? And if you have sample mean and you plus minus this guy, then you're done, right? And the same for the T thing, right? Which I'm not going to repeat. As you can see clearly how it can be done, right? If this is the T, you just give your alpha, your S, your N will give you the number. Is that okay? And this number actually from our example. Is there any question before we end this set of slides? No? So I think you will be ready to do your assignment, which we release next week. I know you're busy, so I asked the TA not to release this week. So have you and let you enjoy the weekend because the due date is based on the day we release, right? So we give you more time. Okay. So if there's no question, then we will be doing a next chapter, okay, which will be unfortunately a rather long chapter. So I hope you are still awake. Oh, here. Hypothesis testing. So since you are tired, so let me draw some pictures to make that you are a little bit better. So remember what we are working on. So we always want to study some population. Something interesting, right? So imagine the population have a guy, number 1, right? And maybe woman number 2, right? And we also have elderly number 3, right? And we also have baby number 4, right? And maybe we have dino number 5, right? So it depends on who you draw, right? And maybe since Halloween, right? So let's have a ghost number 5, number 6, right? Depending on what you draw, right? And the mean will depend on what you draw, right? So the mean, right? Mu in this example will be 3.5, right? We know it already, right? Sigma with some number will be 2. I think 2.6 something, right? Some number there. And but in reality, we don't know mu and sigma square, right? Because that is too large to know. And what we're going to do from last class is, okay, sorry, we randomly grab some people here, and this is known as sample, right? And the sample, we will have sample mean, in this case 1.5, right? S square will be some number there, right? And estimation tells us that as long as we draw this sample is correctly, this will be a good guess of this number. Of course, it never be right, but it can be a good guess, right? And that's what we call estimation, right? Not only that, we can do interval estimate, right? If we know sigma, this will be point estimate, interval estimate. If we don't know, we do this, right? This will be how we guess the mu, right? And that's what we cover in the last topic. So the question would be, that is, we are extending our knowledge from sample to population. Okay, is small to big. Okay, the question now is, can we go back? Can we from big to small? Okay, of course we don't know big, but what do we mean by big to small? Big to small means if we have some claim or some idea about mu, say to make simple, we know some other mu. Can we use the data to see whether this kind of assumption is right or wrong? So this is the test. And this is called the hypothesis. So that's why this topic is called hypothesis testing. Hypothesis is some working assumption on the population. We want to see if the data justify it. You will ask, what are we doing? Is it crazy? No. You go to our accounting class. The accounting is hypothesis testing. You go to audit, hypothesis testing, right? You are not going to check every single inventory in the firm. You're not going there every day. You just go for one day. You are looking at evidence that should not contradict the statement they give you, right? So that's the idea, right? You're looking for evidence. Same in the courtroom. The court system is indeed a hypothesis testing. Why? A defendant in the court, in the beginning, in the British system, as far as I understand, is assumed to be not guilty. And you would have to have evidence that have to be beyond reasonable doubt to say that he is guilty of the crime he accused of, right? So the evidence is the sample. Okay, you want to see the evidence from the data is going to support the hypothesis or the claim you made on the population parameter. Okay, you want to say mu is this or mu is not this. Okay, so for example, one of our classmates bought a white type soya meal. In the front, it said low sugar. Okay, and low sugar is a claim by the manufacturer, and the government will want to see if this is actually low sugar, and it will collect information to see if it is contain less sugar than it claims, or it claims it is a white soil, then it should be from soya milk, right? It shouldn't be just water plus some chemical pretend to be milk, right? So that is something we need to know. right? So that is the idea of this chapter. So it's highly relevant for auditor, highly relevant for the courtroom, and highly relevant for all data analysis. Why? Both estimation and hypothesis testing are the main ingredient when you handle model. Why? You have model, you need to estimate the model. That is estimation. But is the number you estimate the model is useful have to be validated by hypothesis testing. You will see hypothesis testing is the way that after you estimate everything, you want to validate, you want to test it whether it's good before you go. You want to use it. So you can say hypothesis testing is a quality control in statistics. Whenever you estimate a model, you have to go through hypothesis testing before you actually say this model is good. Okay? So that you will see we will do these two procedures when we look at the last two topics, ANOVA and linear regression, which we will do this procedure. We will introduce a model, estimate model, and then you test the model whether they're good or not. And then you can put in the practice. Okay? So this is the two-step. Whenever you go to do statistics, there's always two steps. One, estimate model, and two, do hypothesis testing. Okay? So, is that okay? Okay? Good. So let's start our very long chapter, 120 pages. So you cost us like I think 3 to 4 classes. But you have a holiday, so probably we'll spend 2 weeks, okay, in total. One sample. So this topic is divided in 2 parts. This is one sample. There are 2 samples. And 2 samples will be closely related to what we call A/B testing in the business world. And A/B testing is very often in all the internet industry. Is when you see the new website, new feature, before they implement, they will do A/B testing. A/B testing means that you will see the feature 1 and feature 2. Is a new feature going to be better? And the comparison is what we call 2 samples. You have 2 different samples. You test it. We'll see the improvement one over the other. Okay, but first we do one sample first before we get into something more exciting. Okay, but one sample already a lot uses. Okay, so don't worry about we learn something useless. Everything we learn in this class is basically condensed to 0. Rubbish. Okay, everything is very, very useful. Okay, so hypothesis testing, as I said, is we test a claim supported by data. So if a claim already, beginning with, we start with claim, and we'll see the data support the claim or not. Okay? And we will assume the claim is true until the evidence suggests otherwise. Okay? So same as the courtroom, as I said, you assume that guy is innocent until proven guilty with enough evidence. Okay? So that is the first thing. So we have, as you said, the courtroom. So we start with the null, which is working hypothesis, which is we assume that guy is innocent. And this is the one we denote as X null, X0, or X naught. Okay? It's assumption that we have at the beginning. We want to check it. Okay? Say, for example, the white soya meal, they claim this is the percentage of the sugar. It's a claim we want to test. Or the auditing client tell you that this is the cash in the bank. I have 1 million cash in the bank. You want to check, right? This is a working hypothesis. The alternative is called X1 or XA, right? It's the thing that we want to see the data is going to this direction or not. Okay, it's called the alternative hypothesis. So there's null and alternative. Okay, X1 or X0. So two notation here. So technically, what's hypothesis testing? Hypothesis testing is we specify a rule, okay, when your null hypothesis is reject, one is accept, right? It's like court will be saying specify what kind of evidence we will say the defendant is guilty of his crime or not. What is evident beyond reasonable doubt? For example, in a murder case, right? I don't know too much about law, so correct me if I'm wrong. But if a murder happened, if you are not in the scene, you are in another country. So unless you're Superman or Superwoman, right? You're unable to kill the other guy, right? So that would be the case you would accept as a evidence of innocent, right? If you are in the crime scenes, you hold the weapon and your record with the video, that's likely that it's evident that you reject his innocence, right? So that will be the idea, right? So that will be specified the sample value that is reject. And this hypothesis testing is a big business. So it's a very complicated, as you can imagine. So we will focus on something very simple, okay? So first we will define hypothesis in two types. One is called simple, the other is called composite. Simple means very simple, means that we say population mean, which is our focus, is a particular value. Okay, mu is 3, mu is 4, mu is 5. Okay? A composite is opposite case is you say it's more than one value. So maybe less than 3 is more than one value. It's a lot of value, right? More than 3 is a lot of value. Not equal to 3 is a lot of value. Okay? Equal to some number, just one value. Not equal to some number is a lot of value, right? Not equal to 3 can be equal to any number, right? Just except 3 only, right? And less than 3 can be anything, right? Can be 2.1, 2.2, 2.3, 1, -2 can be a lot. Okay? So why we do that? Will be immediately clear. Because for our class, and also actually for many other undergraduate class, we will assume the following. Null is always simple. Alternative is always composite. Yeah. Right? So for example, when we have alternative, right? Actually, we will divide it ourselves into 3 different types. Either less than, more than, or not equal to. Okay. So the question would be when to use which, right? Because the null is always simple, there's no problem, always equal. The alternative is composite, and composite has 3 types, right? More than, less than, or equal to. You ask when to use what. Okay. The answer will be very easy. So this is our final knowledge point we covered today. If we have no idea, okay, by default, if you no idea, this is the standard, okay? This is the one that you should use if you don't know what to do, okay? You don't know if anything, this is something we want to do, okay? And when we'll use less than? Less than will be used when you would take action when something less than will be important. For example, you are government checking whether someone claim, right? I don't know, the food, right? Has so someone claims it's the milk, right? Milk should have a I don't know, by construction have 80% milk, right? Can at most have 20% water, right? You cannot all water, right? And if has less than that, right? Then you will sue the company, right? Why? Where you have this more than, right? Suppose the law said you cannot have this much of preservatives or coloring in your food. If more than that, you would sue the guy. So then you would more than would be a problem, right? If you audit her, you would be not equal to the problem, right? If the firm claim they have 1 million in the bank, if less than 1 million, you will not be happy. If more than 1 million, also will not be happy as well, right? Because you will have to attest what exactly in the statement, right? More than or less than will not be tolerated, right? So that would be the case, right? So that would be the idea, right? So that would be that would be that would be the thing, right? So more than less than. So if you don't know, right, the harmful will be more than, right? Otherwise, less than. So I think I'll give example here. So if you are a consultant, McKinsey, right, suppose, for a local club, and because of aging society, right, or people go to Shenzhen, right, probably only local club, the age of customer may be increasing, okay? You want to see, the owner want to see if it is more than 45, right? If this is more old people, then probably you want to use the old people entertainment, right? Otherwise, not change. So you want to see now is always simple. The alternative will be more than, right? So that would be you take action if more than. So look for evidence more than, right? Because you don't want to take action if less than, right? So that's why the alternative is more than. Okay. But don't worry too much because usually I would be giving you more than or less than. At least in the sentence, you don't need to guess. Okay. I would explicitly give you whether alternative more than or less than, right? You don't have to guess. But if you have to do on your own, you have to decide. And two-sided, you don't know, right? So the example like this, right? As I said, the firm, someone claim it's 3,000, right? And you want to test it's true. So either mu is 3,000 or not, right? Because either the case is not more than or less than is not, right? Less than, right, is the guy may be cheating for bank loan. More than is evading tax. So you don't want to be in the trouble, either of them, right? So that is the case. So I guess I should stop here because many of you are already tired and also overrun in the past. So let's end our class 1 minute earlier. So I will see you next Friday. Unfortunately, we have holiday on Wednesday. If you are in other school, they have class on public holiday. So luckily, we don't. Okay. So I will see you on Friday.